All right, so you're going to have to forgive the quality of this video because it's not on the dot cam, so I'm not sure how well it's going to work. But I wanted to go over the box problem, the box volume problem with you, if I could. So here's the premise of the box volume problem. It starts out with a piece of square paper that is 24 inches on each side. All right, and we're going to cut a little square out of each corner to be able to make my box. Okay, so let's say I cut this little square out of the corner, and this square is X inches wide on each side. X inches wide, X inches tall. Okay, so I have cut X inches out over here. So this part is no longer 24 inches long. It's 24 minus X. But I'm not just going to cut this one out. I'm going to come over here and cut the same size piece out. So now I've cut out X, a piece of, let's see if I can focus this, sorry. A piece that is X by X square over here. So now it's 24 minus X, but I'm going to do the same thing over here. So now this distance is 24 minus 2 X's. So this distance is 24 minus X. Excuse me, 2 X's. Same thing happens here when I cut out one over here and one over here. Then this distance will be 24 minus 2X. So now I've cut out all my corners, and instead of being 24, remember 24 was all the way across here, we've got 24 minus 2X. So that's what we have now. So now we're going to start folding this to make it into a box. So I'm folding up each of these little flaps on the side. Okay, and when I get finished folding them all up, my box looks something like this, and I'm going to turn it this way so we don't have those. Just ignore these, they're kind of in our way. And so now this distance, remember, is the width of the flap. So this distance is 24 minus 2X. And this distance is a square. This distance is also 24 minus 2X. And when you're doing volume, what you're doing is you're finding the area of the whole base times the height, going up from there. So the whole base is a square. It's 24 minus 2X times 24 minus 2X. That's the area of the base. But volume says length times width, which is area of the base, times the height. So then we have to multiply times the X. So we end up doing 24 minus 2X for this distance times this distance is 24 minus 2X, or this dimension, times the height, which is X. So that's my volume. It's the same as if I said volume equals length times width times height. So this is my function. This is the volume function. I could write that as V of X instead of just V. Okay, and now I'm going to start simplifying it. I'm going to go ahead and do FOIL for these two binomials. So 24 times 24 is, I believe, 576. And then you're going to do minus 24 times 2X, which is negative 48X. And then do the same thing here. Minus 48X minus 48X is minus 96X. And then last times last, negative 2X times negative 2X is plus 4X squared. Now all of that is still times X. So I still have to distribute that X, and I'm sorry for the phone moving all around. So 576 times X minus 96X times X, which is X squared, plus 4X squared times X, which is X to the third. So I'm going to go ahead and rewrite this in descending order with the biggest exponent first. 4X cubed minus 96X squared plus 576X. And that is my function, all simplified, or multiplied out really. That's what's going to go in my graphing calculator. So now let's go there. So in my graphing calculator, I'm going to go to y equals, and I'm going to put 4x cubed minus 96x squared minus 576x. Okay, if I look at this at the standard window, and I deliberately went to the standard window by doing zoom 6, I can't see anything of value. This is not valuable to me. Okay, so we're going to have to figure out what window we need to use to look at this, and there is where it helps to be able to find our domain and even think about the range. Okay, first thing I want to point out here is this is definitely not quadratic because we have an x to the third, it's cubic. And it makes sense because we're multiplying length times width times height. We have 3 dimensions, okay? And each of those dimensions has an x in it. So we're going to have x cubed. It also makes sense because if you think about volume, that's in cubic units, excuse me. Like if I were to measure the carpet in my classroom, that would be square feet. But if I measure the amount of air in the classroom, that's cubic feet. So volume's always in cubic units, and it has to do with being cubed. So back down here, one way to get a better idea of this is just to keep zooming out and zooming out and zooming out. That's not the most efficient way. Okay? I do know it's not going to be a parabola because parabolas, parabolas, even though it kind of looks like one here and it kind of looks like one in that table, parabolas are squared. This is cubed. So a better way is to go to the window and actually set the window based on what we know that the domain and range should be like. Okay, so let's talk about that for a second. It's not very flat anymore, but this is my 24-inch square piece of paper that I cut. This is my x that I cut out. This is x by x. So I cut into this paper x inches. Okay, now the smallest amount of cut I could make, well, I could make maybe a 1/2 inch cut or maybe a 1/4 inch cut, or if I'm using really special scissors, I could maybe make an 1/8 of an inch cut, 1/10 of an inch cut, 50 of an inch cut, who knows? I could make the smallest cut I could possibly make. That means I could go all the way down to 0 for x, but not actually 0. Because if I actually don't cut, then I don't have any corners. So if I could theoretically cut really, really tiny and fold really, really tiny, then I can go almost to 0. So x can go almost to 0 in terms of how small it can get. But look at how big it can get. It doesn't work to say all real numbers because I can only cut so far here. I can't cut 100 inches. Okay, I've only got 24 total. And if I want to make a box, I can only cut to about right here because think about where my corners are going to be. See the black Sharpie lines I just drew? I had to put the phone down to do it. But this is like if I cut a much bigger box. Okay? But eventually these are going to meet in the center, and then there's not going to be any space to be the bottom of the box. Because remember, the bottom of the box, these sides have to fold up from. So if I'm folding up higher, I'm having less bottom of the box. So let's suppose I could make the bottom really, really tiny. How tiny could I make it? Well, how big can I make this? If it has to come from both sides, the farthest it could possibly come is almost to halfway. Halfway is, remember this whole thing was 24, halfway is 12. So it could come almost to 12, but not quite, because then you wouldn't have any skinny little piece up here that I could fold up and make a box. So my domain is 0 to 12, not inclusive. Okay, so that's my domain. It's not going to get to 12, it's not going to get to 0, but it could go right up close to it. Now range, remember that chart? We estimated the top to be at 1024 just by looking at the table of values. So range could be, let's see, the volume could be really, really tiny. I don't know, maybe it could be close to 0. Probably a little bigger than that. But maybe on the upper end, somewhere in the vicinity of 1024, maybe 1050. This is just a ballpark. This is correct, but you weren't asked about range. This is just a ballpark. The reason I need a ballpark, though, is to put in the y min to y max. So if I really want to see this, and I want to see it in the range that it matters to me, that would be on a domain of 0 to 12. Or maybe sometimes we make it a little bit below where we know it's going to go and a little bit above so that we can see it nicely within the edges so it doesn't like come right up to the edge. And for my y min to y max, oh, let's say -10 just so that we can still see the x-axis on the bottom. And for max, this is where it's going to really change things. Maybe 1050. Maybe if you're not positive that was the top, maybe 1100. And then when I press graph, I'll see it now. Actually, I have a scatter plot turned on there. Pretend I don't have a scatter plot turned on. Let's pretend a lot of things. Okay, I said let's pretend a lot of things because I noticed that for one thing, my graph was entered incorrectly. I had put minus 576 instead of plus 576x. So that's why it was over here. And also the scatter plot was on. And also the custodian was coming into vacuum. So we were pretending all of those things weren't true. So this is the actual function correctly graphed. Here's what it looks like. You're not seeing the other part of the cubic because it doesn't matter for our domain. It's over here. All right, so if I wanted to find the maximum of this, I'm going to use the calc function, so second calc. Maximum is 4. Left bound means move this little cursor to the left of where you think the top is and press enter. Then move the little cursor to the right of where you think the top is and press enter. Notice it's not saying this is the maximum, it's telling me other directions. Now the guess is not really relevant here because there's not a couple of maximums here, or maxima, so I'm just going to press enter. And my maximum is when x is 4, that's basically what that's saying, y is 1024. So that table was really dead on. Okay, the maximum value here is 1024. What that means is I get a volume of 1024 cubic inches when the size of piece I cut out of the corner of the paper is 4 inches by 4 inches. So when x is 4 inches, that will be the biggest volume I can get by making a box in this particular way. Now, the next thing it asked me to do was to plot the points from the grid, from that table on the graph at the same time and see how well this fits it. So let's just do that. Okay, here was the chart. It's on page 27 in your textbook. So I'm going to go to stat, and I'm going to put that in so I can make a scatter plot. So I hit stat, and then edit, which means just press enter at this point. And I've actually already put it in. I put the x values in list 1 and the y values in list 2. So here it is. And if I want to graph that as a scatter plot, I go to here where it says stat plot. So I'm going to do second y equals. Notice all of my scatter plots are off right now. I just need to turn one on and make sure it's set up to show that info. So I'm just going to press enter. Turn it on. Where it says type, that's scatter plot right now, what it is on right now. It's also on the correct lists. It's also on list 1 and 2. See that right here and right here? So that's where my info is, so that's perfect. And now when I go off to the graph, I'll see my scatter plot points and my actual function. And it's literally a perfect fit. So that's pretty much the end of the problem. Oh, and last but not least, we didn't talk about, is this a function? Yes, it's a function. Okay, even if we were just looking at the table, what we see in the table implies it's a function, because for each value of x, there's a unique value of y. Looking at the graph, it passes the vertical line test. We also know because it's a cubic polynomial that's going to pass the vertical line test. Cubic polynomials are functions. And that's pretty much all we can do with this particular problem. So I'm glad you watched this video, because tomorrow you just might have another one like it. And now that you know how to do it, it should go pretty quickly. See you tomorrow.